What's up, everybody, and welcome back to OpenStax Algebra and Trigonometry, Chapter 5, Section 3, Graphs of Polynomial Functions. Let's do it. Question number 1, what is the difference between an x-intercept and a zero of a polynomial function? So I actually generally look at these as kind of synonymous because your x-intercept is going to also tell you where the zero of a polynomial function is. But if we want to say explicitly, an x-intercept is where the function crosses the x-axis, and the zero of a polynomial function is when the polynomial function itself, f of x in this case, would actually equal 0. So again, this is actually going to be the same thing in a sense, because when you have a x-axis and you have a polynomial, right, it's crossing the x-axis here. That means that's an x-intercept. But that value of x at the point where it crosses, the function value is going to equal 0. So you can kind of see there's some overlap there. So that's how you do it. Boom, done. Explain how the intermediate value theorem can assist us in finding a zero of a function. Now, this is a little infographic that I've made to explain what the intermediate value theorem is. And essentially, it's this, right? If we have a function and we're assuming it's continuous, and that means that we can trace the entire function without lifting our pencil, right? It's all just connected together. And what the intermediate value theorem says is if I have an interval, right, and I'm starting at A and I'm going to B, and I know that this is a function value, right? That's the x values, A and B. That function value, meaning sort of like the y value that's related to this point, and the y value that's related to this point, aka f of b, right? So if I have a interval from A to B, k is a number between fa and f of b, right? So k is, let's say here's f of b, here's f of a. Let's say k is here, right, at this level. There must be, the intermediate value theorem then therefore says there must be a c value such that f of c, right, some c in between a and b such that f of c equals this k value. So what does that really mean? It basically means that, you know, if I have a starting point here and here, and this is smooth and continuous, there must be some point in the middle in this interval that has a function value that is equal to a function value in between the function values of the endpoints. So that's essentially it. Now, let's relate this back to finding a zero of a function. This becomes more relevant if we have a function like this. Let me show you. Now, if I have a function like this in red, and I say my interval is from here, let's say A to here, B. And where this becomes relevant is this says that, well, wait a minute, I know that f of b up here is positive. I know that f of a down here is negative, right? Because it's below the x-axis. Therefore, a zero, at least one zero, must exist between a and b because 0 is in between f of a and f of b, right? F of a is negative, f of b is positive. And because it's a smooth continuous function, there must be a 0 on this interval. That's how you do it. Boom, done. If the graph of a polynomial just touches the x-axis and then changes direction, I call this a bounce. Some people say touch. What can we conclude about the factored form of the polynomial? So just so you can see what we're talking about, let's say we have a polynomial like this. It touches the x-axis here and then it bounces up, right? Let's just say this is the polynomial. I'm just making this up. So let's say it touches the x-axis at the point of 4, right? So that is a coordinate of 4, 0. What that means when we have a bounce, not a penetrate, right? Penetrate would mean it's coming through and it's coming out the other end, right? We have a bounce. What this means is when you factor this, right, since 4 is a 0, x minus 4 would be one of the binomials when you factor. That would mean that this binomial is raised to an even power. So it could be raised to the second power. It could also be raised to the fourth power, sixth power, eighth power, etc., etc. So that's what it means when you have a bounce. Done. For this one, we're finding the t-intercepts, and the good news is it's already factored. And what we're trying to do when we're finding the t-intercepts, or x-intercepts, but in this case t, is when we're going to get certain values of t that are going to zero out the entire function. Now, because it's factored, it's pretty nice. All I have to do is say, hey, what value of t is going to make this binomial go to 0? That's -2. It's going to give me a value of -2, 0, right? We already know that. What about for this one? That's going to be 3, right? 3 minus 3 is 0. It's going to zero out the entire thing. And what about this one? It's going to be -5. That's the answer. Done. For this one, once again, it's in factored form. We've got 1, 2, and 3 different pieces. So since these are all multiplying each other, now I'm trying to find the zeros, I just have to find values of t that zero out each one of these individual expressions. So for 2t, it's just going to be 0. So we have 1, 0 at 0, 0. For t minus 3, it's going to be positive 3 because 3 minus 3 is 0. So we got 3, 0. And last but not least, for this one, it's going to be negative 1. Negative 1 plus 1 zeros out. So we got negative 1, 0, boom, done. For this one, to find the zeros, we got to factor. But the first thing we want to do is see if there's any GCFs. And there is a GCF. So we're going to factor out 4t squared because that is common to every single one of these terms. If I pull it out of the first term, I'm just left with a single t squared. If I pull it out of the second term, aka divide the second term by that, 12 divided by 4 is 3. T cubed divided by t squared is just regular t. And then here we divide it by 4t squared. We just get a 10 or negative 10. Now let's see if we can factor this inside further. So we've got multiplying to negative 10, adding to positive 3. That would be a positive 5 and a negative 2. They multiply negative 10, add to positive 3. And then now we look at the zeros. What's going to zero this one out? That's going to be 0. So it's going to be 0, 0. What about this one? That's going to be negative 5, 0. And what about this one? We've got 2, 0. There are the zeros. Boom, done. Again, let's start this one by factoring out the GCF, which will be simply x. Now let's factor this trinomial a little bit more, and we know we start with x and x to get that x squared, and then what two numbers multiply to negative 20 add to 1? That would be positive 5 and negative 4. Now we can get the zeros. This one zeroes out at 0, right? This one zeroes out at 4, 4, 0, and this one zeroes out at negative 5. And why? Because negative 5 plus 5, 0. 4 minus 4, 0. 0 in there is just 0. These are your x-intercepts. Boom, done. For this one, we're going to start to see, is there a GCF? And there isn't a GCF. So instead, with 4 terms, I'm going to try and factor this, and I'm going to use factoring by grouping. So we're going to kind of group the first terms together and the second terms together. Now, out of the first two, I can factor out an x squared, right? And I'm left with x plus 1. That is these two, right? If I multiply that out, I get x cubed plus x squared, so that's cool. Out of the second group, right, out of these two, I'm going to factor out a negative 4. And I'm doing that strategically because now I have an x plus 1 left inside, right? Negative 4x minus 4, still the same. So now why is this great? Because I have an x plus 1 that's common to both. Now I can factor the x plus 1 out of both of these terms. So I pull the x plus 1 to the front, and I'm left with the x squared and the minus 4 here, like so. Then I can factor this because it's a difference of squares. So I get x plus 1 times x minus 2x plus 2. And this gives me 3 potential x-intercepts, right? When is this going to zero out? When x equals negative 1. When is this going to zero out? When x equals positive 2, right? 2 minus 2 is 0. When is this going to zero out? When x equals negative 2, right? Negative 2 plus 2 is 0. Those are my 3 x-intercepts. Boom, done. For this one, there is no GCF, so we got to go straight to factoring. And because there's 4 terms to the third power is the highest, usually this means, hey, we should factor by grouping, so let's give it a shot. From the first two, I'm going to factor out an x squared, and what's left inside is 2x minus 1, right? And you can see that if I redistribute this, I'd get 2x cubed minus x squared back here, so we know we did it right. For the second one, I'm going to factor out a negative 4. And in general, if I see this as being a negative term, I'm usually going to try and factor out a negative. But you could try factoring out a positive 4. You would see that the binomials you'd factor wouldn't match up. So you'd be like, all right, let me try that again. When you do it with negative 4, watch what happens. So then I get a positive 2x in here, and I get a negative 1 there, because negative 1 times negative 4 brings me back to positive 4. Now these two match, and that's what I want, because now I can pull them out, 2x minus 1, like so, and I got the x squared minus 4 in here. Again, we got a difference of squares, so I'm going to factor that difference of squares. Check it out. That's going to be x minus 2, x plus 2. And you can FOIL this out to prove it if you're like, hey, I'm not sure if that's right. It becomes x squared, positive 2x, negative 2x. Those go away, and then negative 4. So you can see it's the same. Now we got 3 zeros. When is this going to zero out? When x equals 1/2, okay? 1/2 times 2 is 1, minus 1 is 0. Here it's going to just be 2, 0. And here it's going to be negative 2, 0 for the win. Boom, done. In this one, once again, we're checking for a GCF. We got a nice GCF of 2. It's little, but it's going to help. Now we've got a polynomial that is factorable. So check it out. I'm going to factor it just like a typical quadratic, except for its x to the 4th power. So what I'm going to put up front here instead of x is x squared. And then what two numbers multiply to -4 add to +3? That's going to be +4 and -1. For this binomial, we have a sum of perfect squares. Just remember that you cannot factor a sum of squares. It looks like, man, you want to be able to factor it, but you can't. So that one's good to go. The 2 is obviously chilling. But here we've got a difference of squares. That is factorable, so check it out. It becomes x minus 1 and x plus 1. And now we've got our positions for zeros. So a sum of squares, you actually cannot zero this out because think about it, you'd need a negative number, but an x squared is always going to be positive. So we don't worry about that binomial. Don't worry about the constant. But here we zero out at 1, and here we zero out at -1. So those are your two x-intercepts. Boom, done. For this one, we're going to start with the GCF of x squared. So I'm going to factor that out of everything. I have an x to the 4th left. I have a -2x squared left. And then I have -3. Again, pulling out an x squared out of each of them, it's like dividing by x squared. Now we're going to factor this trinomial as if it was a quadratic. So because it's x to the 4th, my first two terms are going to be x squared. And then we ask the question, what multiplies to -3 and adds to -2? That's -3 and +1. So as I mentioned in a previous problem, a sum of squares we cannot factor further. So you're good to go there. A difference of squares is factorable. However, this is not a perfect square. So it's a little dicey, but I'm going to show you how to do that in 1 second. Last but not least, we got this guy. That's a standalone term. We know that it's going to zero out at 0. So we already know we got 1, 0 at 0, 0. That's our first x-intercept. Now this one, we're really trying to figure out when this is going to equal 0. And like I said, it's not a nice difference of perfect squares, so we can't do our typical factoring. But I can take this equation and solve it and get my other two zeros. So I'm going to add 3 to both sides, and then we're going to take the square root. Now remember, when you take a square root, you have a positive and a negative radical. So these are our remaining zeros. We got rad3, 0 and negative rad3, 0. So those are your 3 zeros. Boom, done. For this one, let's start with the GCF of x. I'm going to factor that out. Now we can factor this like a quadratic, so check it out. Because my leading term is x to the 4th, I'm going to have x squared in the front, x squared, x squared. Then we ask the question, what two numbers multiply to +4 add to -5? That would be -1 and -4. And guess what? We got two beautiful, perfect difference of squares here and here, so we can factor both of those. So x squared minus 1 factors to x plus 1 and x minus 1. X squared minus 4 factors to x minus 2 and x plus 2. So it looks like we have 1, 2, 3, 4, 5 potential zeros. So the first one for that x out there is going to be 0, 0. For this x plus 1, it's going to be the opposite of that, which is -1, 0, right? -1 plus 1 zeros it out. For this one, it's going to be +1, again, because plugging in 1, it gives you 1 minus 1, which zeroes out the function. Here we have +2, and here we have -2. So we have 5 x-intercepts. Boom, done. So here we're going to use the intermediate value theorem to show that there must be at least one 0 between 2 and 4. So what I'm going to do is I'm going to first figure out what is the function value at 2. So I'm going to plug it in. That's 2 cubed minus 9 times 2, which is 8. 2 to the 3rd is 8, minus 18, which is -10. So my function value at f of 2 is -10. Then I'm going to plug 4 in. I got 4 to the 3rd minus 9 times 4. That is 4 times 4 times 4 is 64 minus 36. And therefore, f of 4 equals a positive 28. Now, because we have one value at a negative, right? So we got f of 2 is -10. Then we got f of 4 is positive 28. This shows from the intermediate value theorem that we must have a 0 in between because this is a polynomial. All polynomials are continuous. So we don't have to worry about a discontinuity like, hey, it goes from here and then it just pops up here and there's no 0. We don't have to worry about that. We know it's going to come through the x-axis at least at one point. So this proves from the intermediate value theorem that we have at least one 0 on this interval. Boom, done. For this one, once again, we're using the intermediate value theorem, and we're going to plug and chug these values because the interval is from 1 to 3. So if I plug in 1, right, I get 1 to the 4th with a negative in front plus 4. That's just 1 negated, right? We applied the negative after the fact. Negative 1 plus 4 is 3. So f of 1 is 3. Then here we plug in 3. We get 3 to the 4th, and then that negative's added on at the end again, plus 4. So that 3 to the 4th is 81 with a negative plus 4 gives us negative 77. So f of 3 is negative 77. Again, because of the sign change, we know there has to be at least 1 0 from 1 to 3. And we can illustrate that by showing that f of 1 is up here at positive 3. F of 3 is down here at negative 77. Obviously, it's not to scale. But assuming it's continuous, which it must be because it's a polynomial, it must be continuous, therefore it must pass through the x-axis at least once in that interval. Boom, done. Once again, we're using the intermediate value theorem here, and we're going to plug in for 0.01 and 0.1 and see what we get. So 0.01 to the third power is actually going to be 0.000001. It's really small. And then 100 times 0.01 is 1, so that's minus 1 plus 2. So you can see, I mean, this is almost negligible. It's so small. The bottom line is we're getting a positive value, but I'm going to tell you exactly it's going to be 1.000001 is f of 0.01. Now I'm going to plug in 0.1, so we have 0.1 cubed minus 100 times 0.1 plus 2. 0.1 cubed is really small as well. It's 0.001. 100 times 0.1 is 10, so minus 10 plus 2. So this, again, is so small, it's kind of negligible. We know we're going to get a negative answer, but just to be precise, this is going to equal 7.999. Negative 7.999. So we see that f of 0.01 is positive. F of 0.1 is negative 7.99. So again, because of the sign change, we've proved that there must be at least 1 0 on this interval. Boom, done. So for this one, to find the zeros, we have to get it into factored form, but it's already in factored form, which is great. And then we just got to figure out what values of x are going to zero out each of these different pieces that are all multiplying each other. Because if 1 goes to 0, the entire thing goes to 0. So for the x squared, it's just going to be 0, right? Plug in 0, it's going to zero out the entire thing. For 2x plus 3, it's going to be negative 3/2. And if you're not sure how to get there, you can take that binomial and set it equal to 0 and isolate like so. 2x equals negative 3, divide by 2, and we get another 0 of negative 3/2. And then last but not least, we get a 0 here of 4, right? And these zeros, their multiplicities can be determined by the exponent of that term, you know, where we got that actual 0 value. So we got a 0 from the x squared that has a multiplicity of 2 because it's got an exponent of 2. This one has a multiplicity of 5 because, again, of this exponent here. And this one, 4, has a multiplicity of 2 because of that exponent there. Boom, done. So for this one, we're going to start by factoring this inside, and that becomes x plus 2. And it's actually squared because this is a perfect square trinomial. You can verify that if you did x plus 2 times x plus 2, because 2 is what adds up to 4 and multiplies to 4, right? So it's a perfect square trinomial, so it can be factored like so. That means we've got 2 zeros, one at 0 and another one at negative 2. Now, when we're talking about the multiplicities, again, it's based on the exponent. So the exponent here is 2, so this one has a multiplicity of 2. This one does as well because it's got an exponent of 2, so they both have a multiplicity of 2. Boom, done. So for this one, we can't do anything further with this binomial. It's already good to go. This one we need to factor. And what does it factor to? So again, what two numbers multiply to 25 add to negative 10? Well, it's negative 5 and negative 5. That means this is a perfect square trinomial, meaning we can write it as x minus 5 squared. And then we got this one, 3x plus 2 to the 5th power. Now we got it factored. Now let's find the zeros. So we want to know, when is 3x plus 2 going to equal 0? So we subtract 2 from both sides, divide by 3, and we got a 0 at negative 2/3. We also have a 0 here when x equals 5, right? Because 5 minus 5 is 0, so that one we can just tell right from looking at it. Now the multiplicities. So since this one that gives a 0 of negative 2/3 is to the 5th power, we have negative 2/3 with a multiplicity of 5, and then 5 with a multiplicity of 2 because of that exponent. Boom, done. For this one, we're going to start by factoring once again and looking for a GCF, which there is, of x to the 4th, because all of these can be divided by x to the 4th. So let's pull that out. And what's left is x squared minus x minus 2. Why? Because I divided each of these terms by x to the 4th. And if I redistribute it, you see we come back to the original trinomial. That's how we know we've done the factoring correctly. Now I've got this nice quadratic. I'm going to see if I can factor that. So what two numbers multiply to negative 2 add to negative 1? That's going to be negative 2 and positive 1. Now we can get our zeros. So this is going to have a 0 of literally 0. That's what's going to zero this out with a multiplicity of 4. This is going to zero out when x equals positive 2, right? 2 minus 2 is 0. And since there's an exponent of 1, this is going to have a multiplicity of 1. Last but not least, this is going to have a 0 of negative 1, right? Because negative 1 plus 1 is 0, with a multiplicity again of 1, because there's an invisible 1 exponent in front of that binomial. Boom, done. Here we got a GCF of x to the 3rd power. It's common to all, so we're going to factor that out first. And then we have 4x squared, right? If you take an x to the 3rd out of x to the 5th, you have x squared left, minus 12x, because I'm pulling out an x cubed, and then plus a 9. Now we want to see if we can factor this guy. Now, this happens to be a perfect square trinomial, but we're going to use the star method to verify, just to show you an easier way to factor. So we got a, b, and c. The a, which is 4, goes here and here. A times c, which is 4 times 9, which is 36, goes up top. And then the b goes down here, which is negative 12. And then we ask the question, what two numbers multiply to 36 add to negative 12? That would, of course, be negative 6 and negative 6. Then we simplify. That's 2, negative 3. Simplify like a fraction, right? It becomes 2 over negative 3. Now we got the two values that we can use to factor this. So check it out. It becomes 2x, that number on top, minus 3. And then again, 2x minus 3. Or 2x minus 3 to the 2nd power. And now we got our two zeros, right? We got a 0 here. What is going to make this one go to 0? Well, simply 0. And what's the multiplicity? It's that exponent, so it's a multiplicity of 3. What about here? What's going to zero this guy out? If you're not sure, you can again set it equal to 0 and then isolate x. So we're going to add 3 to both sides, and then we're going to divide by 2. And that's going to be 3 over 2. If you want a little shortcut, you take the opposite of this value and then divide by that coefficient. So it's positive 3 over 2 is the other 0. And what's the multiplicity here? It's that exponent, which is 2. So multiplicity of 2, boom, done. For this one, we're going to see if we have an additional GCF that we can pull out of this trinomial, which we can, which is x squared. So check this out. When I bring out the x squared, it's going to multiply the x to the 4th, and it's going to become x to the 6th. And then I've got 9x squared minus 12x plus 4 left inside. So again, because I have a leading coefficient, I'm going to factor it using the star method. So I got 9, that's my a term up top, 9 times 4, which is a times c, which is 36, goes up here. And then my b term, negative 12, goes down here. So what two numbers multiply to this and add to this? That would again be negative 6 and negative 6. Then we simplify this like a fraction, divide by 3. It becomes 3 over negative 2. Same with this side. So it looks like you can see it's a perfect square trinomial because we have the same binomial, 3x minus 2 and 3x minus 2, repeated. So I can simplify this in factored form as 3x minus 2 repeated twice, aka squared. Now we can get the two zeros. First, we have a 0 of literally 0, right? What do we plug in here to zero it out? Is 0 with a multiplicity of 6. So I'm going to write that here. And then with this one, we have a 0 of, again, I can take the opposite of this divided by this, or if you like, we can just be like, okay, what's going to zero this out? Meaning, when will this equal 0? So I'm going to add 2 to both sides, and I'm going to divide by 3. This is another way to do it. So we get 2/3. So the other 0 is 2/3 with a multiplicity of 2 because of that exponent. So there's your answer, done. So for this one, we want to graph it. And to graph it, we want to identify all of the x-intercepts as well as the y-intercepts first. So the x-intercepts are, again, those zeros of the function. What's going to zero this out and what's going to zero this out? And I can see that for this one in front, the binomial, it's going to be negative 4, right? Because negative 4 plugging in here plus 4 is 0. And for this one, it's going to be 1. So 1 comma 0. And then what's our multiplicities? So this one is going to have a multiplicity of 1 because there's no exponent. This one's going to have a multiplicity of 2 because of that one. Next, we find the y-intercept. That's when x equals 0. So we're going to plug that in. 0 plus 4 is 4. 0 minus 1 is negative 1. But when you square it, it's positive 1, and then 4 times 1 is 4, so there's my y-intercept. We also want to think about the end behavior, and the end behavior can be determined by figuring out, what is the degree of this function, or what would that leading term be? Well, if I FOILed this out, right, I know I'm going to get x squared minus something plus something, whatever, but the leading term here is going to be x squared, and then you're going to multiply that by that x out there. So what are we talking about? We're talking about a significant leading term of x cubed. That's going to be what we use to inform our end behavior. So for example, as x goes to infinity, right, for an x cubed, the rest of the things kind of become irrelevant. I'm going to show you why. Then what's the function value of the entire x cubed going to go towards? Well, as x goes to infinity, then that big number cubed is going to be going to infinity as well. So f of x will be approaching infinity as well when x approaches infinity. When x approaches negative infinity, however, a negative number, when it's cubed, negative times negative times negative, will be negative, but it's going to get bigger and bigger in terms of like actually getting smaller and smaller, but becoming a larger absolute value, right? So we're approaching negative infinity as x goes to negative infinity. So now we got the components to kind of put this together, and I'm going to show you how. So we got the x-intercepts of negative 4 and 1, 0 right there. We got a y-intercept of positive 4, 0, positive 4. And now we're going to see how the multiplicities affect everything. So this one has a multiplicity of 2. This one has a multiplicity of 1. By the way, we have our end behavior, right? As x goes to the left, it's going towards negative infinity, to the right, positive infinity. So let me show you what that looks like. So to the left, it's going down towards negative infinity. And then going to the right, it's going towards positive infinity. So something like this. This is just an approximation. And then in the middle, let's look at these zeros. This has a multiplicity of 1, so it's going to penetrate. It's going to go right through, and we're going to touch that y-intercept like here. And then it's going to come down, and we got this other x-intercept that it's got to touch. And here, it makes sense that it's going to bounce. It's not going to penetrate because it has an even multiplicity, so it's going to bounce. So this is a pretty decent approximation of the graph. Boom, done. For this one, let's start by finding the zeros, aka the x-intercept. So it's where we're going to zero these values out. So it's going to occur at 3, 0. And again, it's going to have a multiplicity of 3. And this one is going to be at 2, 0. That's again, our x-intercepts, right? And this one has a multiplicity of 2. Now for our y-intercept, we can just find that by plugging 0 in for x. So you plug it in here. 0 minus 3 is negative 3 cubed is negative 27. And here, 0 minus 2 is negative 2 squared is positive 4. So 4 times negative 27 is negative 108. Last but not least, we can see that this is going to be an x cubed for your leading term and an x squared for this one. And when you multiply them out, it's going to be x to the 5th. That's going to be the leading term, and therefore the leading term goes to the 5th power. The coefficient is positive. It's 1. So what does this mean? So for the end behavior, it means as x gets really, really big, meaning as x goes to infinity, the function value is going to go to infinity. Think about plugging in big numbers in for x to the 5th. 100, 1,000, a million. It's just going to multiply by itself 5 times. It's going to get even bigger. So f of x is going to go towards positive infinity. Likewise, as x goes to negative infinity, you're going to have a negative to the 5th power. It's going to get really, really negative, aka it's going to approach negative infinity. So now we have enough data points. And what I'm going to do is, because this graph kind of looks like it doesn't include negative 108 because of the way the y values are scaled. And this is the cool thing. You can be pretty flexible with these graphs. We can just change this. And I'm going to arbitrarily put a negative 108 right here because we need to include that value. So that's my y-intercept. And the scaling, don't worry about it so much. Usually, it's not going to be, we're not trying to get the most precise, most accurate graph. We just want to get the critical points and map it accordingly. So this is going to be just fine. And then we have our nice x-intercepts at 3 and 2. And again, with an odd multiplicity, it's just going to go right through, boom. With an even multiplicity, it's going to bounce. Now let's next apply the end behavior. So as it approaches infinity to the right, it's going to approach infinity for the function value. So we know it's going to kind of go up like this. And then as we go to the left, right? And since the y-intercept is the leftmost point, as x goes to negative infinity, we're going to go to negative infinity for the function value. So we're going to be going down here like this. And then this is going to be coming up, 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 up. And then when we get to that 2, notice it's a multiplicity of 2, so it's a bounce. So we want to indicate that by dipping down, and then it's going to go up, and then a multiplicity of 3 at 3, 0, it's going to penetrate through. And so we've indicated that. Now, there's different ways to draw this graph, and you might say this dip right here is a bit exaggerated, consider the scaling, but I'm drawing it that way to show that there is a bounce, and then it kind of goes back up through, which I think is what exactly you're going to want to show in your work for your teacher. So that's how you do it. Boom, done. For this one, let's start by finding our x-intercepts. So the x-intercepts are going to occur when these are going to zero out. So for this term right here, the value is going to be 0. And of course, you plug it in, it's going to zero it out. So that's one x-intercept. We got another x-intercept when this is going to zero out at -2. And we got another x-intercept here where this is going to zero out at 4, right? 4 minus 4 is 0. And all of these have a multiplicity of 1. There's no exponent, so that's pretty nice. Now we want our y-intercept. Well, the nice thing is, this is also in a y-intercept. It's a double. It's an x and a y. So we didn't have to worry about the y-intercept. So we got 0, 0, -2, 0, and 4, 0. Next, we want to get the end behavior. So if you kind of multiply these out, right, just looking at the leading term, what's it going to be? It's going to be -3x times x times x, which is going to be -3x cubed. Now, this negative is important because as x approaches positive infinity, what's going to happen to the function value? Well, x is going to get really, really big. You're going to cube that large number. It's going to get bigger. But then at the end, you're multiplying by a negative. So it's going to be negative, which means as x approaches positive infinity, the function value is actually going to go negative towards negative infinity. Conversely, when x goes to negative infinity, let's imagine that. Let's imagine -10 in there, right? -10 cubed is -1,000, but then you multiply it by -3, it's positive 1,000. So you see as we go deep into the negative x values, we're actually getting big with the function values. So as x approaches negative infinity, the function value is going to approach positive infinity. Okay, so now let's draw in the end behavior. So as x goes to the right, it's actually going down. As x goes to the left from here, it's actually going up. And now let's fill in the middle. And again, we're not going to be so specific in terms of where we're landing on the y-axis in terms of the dips and the hills, but we're just going to connect the dots. So because they all have a multiplicity of 1, we're always going through, penetrating, penetrating, and penetrating. And that is a great representation of this graph. Boom, done. So for this one, we're actually taking the graph and we're trying to write a polynomial expression. So I want to show you how we're going to do this. We're going to start by looking at these zeros. We got 1, 2, and 3. So we got a 0 at -3. So again, in factored form, -3 should zero this thing out. Well, that would happen if we had an x plus 3, right? Because then -3 plus 3 is 0. We also have a 0 at -1. So that would make sense for an x plus 1 because you plug -1 in, you're going to get a 0 there. Boom. So then, and we also have 0 at 3. So we're going to have x minus 3. So basically all we're doing is we're saying x minus whatever those x-intercepts or zeros are. Now, the last thing to note is that there could be some sort of a multiplier here, an a value. So let's just put in an a there. Now, how do we determine this a? Well, we actually have a third point that's really important. That's our y-intercept. So we can actually plug in that y-intercept of 0, 2 like so, right? 0 plugs in for x, 2 plugs in for the function value. So again, 0 plus 3 is 3, 0 plus 1 is 1, 0 minus 3 is -3. Now we can simplify. So we have a times 3 times 1 times -3, which is -9. And then to isolate, we divide by -9. And there is our a value, -2/9. So going back to the f of x, if we want to write it in final form, we have -2/9 for the a value times x plus 3, x plus 1, and x minus 3, boom, done. So for this one, we're going to start by identifying the zeros, of which there are 2, right? So that means we've got our standard equation with an a in front because we don't know what that coefficient's going to be. And then we have x minus that 0, x minus -2, aka x plus 2, and then x minus 3. So this is our starting point. Okay, now with that, we've got this laid out. We want to pay attention to the multiplicities because here it goes through, no problem. It's probably a multiplicity of 1. Could be 5, could be 3, an odd number, but we're just going to go with the assumption of 1. And then here it bounces. It doesn't penetrate. So this is an even multiplicity. Let's assume it's a multiplicity of 2. All right, now let's solve this a value by looking at this y-intercept of -3, aka 0, -3. Now we're going to plug and chug, plug 0 in for x right here, and plug -3 in for the function value. Let's go. So 0 plus 2 is 2, and then we're squaring it. 0 minus 3 is -3. 2 squared is, of course, 4 times -3 is -12. So -12a equals -3. Divide by -12 and it simplifies to 1/4, which means our final expression is 1/4 x plus 2 squared, again with that good multiplicity, x minus 3, boom, done. So for this one, we're just trying to find the zeros and the corresponding multiplicities. So check it out. I've got a 0 occurring at -4, right? A 0 occurring at -2, I got a 0 occurring at 1, and a 0 occurring at 3. Again, this is just where it crosses the x-axis. It's where the function value is 0. My multiplicities are going to depend on whether it goes through, aka penetrates, or if it bounces. Now, all of these go through. There's no bouncing, so there's penetration on every single one in terms of the x-axis. So these are all going to have a multiplicity of 1, boom, done. So for this one, we've got zeros at -2 and 3, aka where it touches the x-axis once again. So we got -2 and we got 3. Now, they both bounce. They don't penetrate, they bounce, which means they're going to have each a multiplicity of 2 for both of them. Boom, done. So here we're meant to take this information about the zeros and the y-intercept to create an equation. Let's do it. So we got our 3 zeros at -2, +1, and 3. So I'm going to make binomials for each of those. So when it's at -2, it's x minus -2, which is +2, x minus 1, and x minus 3. We're always subtracting those zeros, those x-intercepts, etc. And then we have an a value. That is going to be our constant that's going to be multiplying everything. And by the way, the fact that this is degree 3, this works out with what we have, right? X times x times x, that's going to be to the 3rd degree, x cubed, etc. So now how do we find this a value? We use this last point and we plug and chug. I plug -4 in for the function value and 0 in for x. So then 0 plus 2 is 2, 0 minus 1 is -1, 0 minus 3 is -3. 2 times -1 times -3, that's +6. So then we divide by 6 and we get a equals -4 over 6, reducing to -2 over 3. Now we finalize the equation. So again, we got our a value with -2/3, and then we got that x plus 2, x minus 1, x minus 3 for the win. Boom, done. So this one, we've got 3 different roots. We've got 3, 1, and -3 with varying multiplicities. So let's check this out. Again, we're going to start the same way with our a, and then we've got the x-intercepts or zeros in the parentheses. And for 3, we've got x minus that value, x minus 3 for 1, x minus 1. And for -3, x minus -3, which is x plus 3. Now let's put in these multiplicities. So a multiplicity of 1 is just chilling because we got a 1 there. That doesn't really change anything. But for a multiplicity of 2, that means we add an exponent here and here. Last but not least, we use that y-intercept to solve for this missing constant of a. So I'm going to plug in 0 here, here, and here for all the x values. And then 9 is going to go in here for the function value. So 0 minus 3 is -3, 0 minus 1 is -1, 0 plus 3 is 3. Now we apply the exponents. -3 squared is 9, -1 squared is 1, and then times 3. So that gives us 27. So 9 equals 27a. I know the a looks like a 9, but that's an a. Last but not least, divide by 27, and that would be 9 over 27, simplifies to 1/3. So our final equation is 1/3 times x minus 3, x minus 1. Of course, both of those are squared because the multiplicity of 2. X plus 3, boom, done. So for this one, we're going to start and look at these zeros. So I got 1 at 1, 1 at 3, and they're saying it's a double 0 here and a triple 0 here. That's going to relate to the multiplicity. So again, we have a constant that we don't know what it is, an a value. Then we got our x minus 1. They said that's a double zero. That means a multiplicity of 2 or an exponent of 2. And a triple zero at x minus 3, right? We take that 0, we subtract it. So then we got an exponent of cubed here. Now to find the a value, we use this point and we plug in the x values and the y values for the function, and let's go. So I plugged in 2 for x, and we got 2 minus 1 is 1, squared is 1, 2 minus 3 is negative 1, cubed is negative 1, and so it's 1 times negative 1 times a equals 15. That's negative 1a equals 15. That means a equals negative 15, right? Negative a is 15. Negative 15 is a. And then now we get our final form. So we got the negative 15 in front, x minus 1, x minus 3 with the exponents in place. Boom, done. So here we got a 0 at negative 3, negative 2, and 1. And we got a y-intercept at 0, 12. And we're going to assume, because it doesn't stay, we're going to assume multiplicities of 1 for everything. Plus, if we have a degree of 3, that makes sense that they're all going to have a multiplicity of 1, 3 zeros, third degree. So let's check it out. Again, we have an a constant that we don't know what that is, but we're going to figure that out shortly. And then in here we have x minus negative 3, aka plus 3, x minus negative 2, aka plus 2, and x minus 1. Now to solve for a, we're going to use our y-intercept. We're going to plug 0 in for all our x values, as that is the x value, and 12 in for the function value. So we got 0 plus 3 is 3, 0 plus 2 is 2, 0 minus 1 is negative 1. 3 times 2 times negative 1 is negative 6. Divide by negative 6 like so, and we get a equals negative 2. With a final function of negative 2, that's the a value, right? I'm just plugging that in here, and then everything else stays the same. And there's your answer, boom, done. Here we've got a 0 or a root, same thing at 1/2, and a 0 at 6 and negative 2. Now this has a multiplicity of 2, and these other ones have a multiplicity of 1. So let's put in the ones with multiplicity of 1 first. That is x minus that, x minus 6, and x minus negative 2, which is x plus 2. Those are both going to be raised to the first power. And then what about this one? This is going to be raised to the second power. Now, we could do x minus 1/2. That's fine. But the other way we could do this is 2x minus 1. And I'm going to lean towards that because that way I don't have a fraction in here. It's going to be a little bit easier to evaluate. And again, you can see that this works because if I plug 1/2 in here, I get 2 times 1/2 is 1 minus 1, boom, done. Now again, we have an unknown constant that we have to solve for by using the y-intercept. So we're going to plug 0 in here, here, and here, and then plug in the 18 for the function value, and let's go. So when we plug 0 in, I get 0 minus 1 is negative 1, 0 minus 6 is negative 6, 0 plus 2 is 2. 2 times negative 6 is negative 12, times negative 1 is positive 12. So we get 12a equals 18, and when we divide both sides by 12 to isolate for a, we get a equals 18 over 12, which simplifies by dividing by 6 on top and bottom to 3 over 2. And then our final function is f of x equals that a value, and then everything else stays the same. And there's your answer, boom, done. So for this one, we're going to use a calculator to approximate the local minima and maxima, as well as the global min and global max. So we're going to use Desmos to solve this. Now the question is, what is a local max and what is a local min? A local max is the top of a mountain, top of a hill, which we have right here. So you can see it. So this is occurring at negative 0.577. We'll round up to the nearest hundredth. And the y value is negative 0.615. So we'll say negative 0.62. And the local min is occurring here. That's the bottom of a valley. That's at 0.577 and negative 1.385. And we'll round those up. Now, what about a global min and a global max? That's the absolute highest value and the absolute lowest value. But as you can see with this function, it continues on to infinity, positive infinity to the right and negative infinity to the left, meaning there is no global max, there is no global min. It goes on and on forever in both directions. So our final answer is 0.58, negative 1.38 for the local min, negative 0.58, negative 0.62 for the local max, no global min, no global max, boom, done. So for this one, I'm going to once again plug it into Desmos to find all of these values. So for this one, I can see a local min right here. It's the bottom of a valley, as we say. Local max is like a top of a hill. There is none. It just looks like it goes up, kind of like a parabola, right? So I only see a local min, and this local min is also a global min because it is the absolute lowest point of this function. I don't see a global max because it goes on in both directions to positive infinity. So in this case, we can call that local min a negative 0.63, negative 0.47, as well as the global min, no local max, no global max, boom, done. For this one, we're going to graph it on Desmos, and then we're going to find each of these values if they exist. So for this one, for a local minimum, we only have the bottom of the valley. We don't have a local max, and we don't have a global max either because it goes up to infinity forever and ever in both of these directions. So it would be 0.75, 0.895. And because this is the lowest point of the function in general, it is also a global minimum. So there we have it, a local min that is also our global min, no local max, no global max, boom, done. So for this one, we're going to make an f of x function, and we're going to start with those x-intercepts. Now, of course, this one looks like it's going through at negative 200. So it's x minus negative 200, which is the same as x plus 200. And this one is at 500, so it's x minus 500. But the thing is, this is a bounce, and this is a penetration. So the penetration would just be, we can say an odd degree, but they said the least degree. So we'll just say to the first power. This one will say to the second power. Okay. Now we need to figure out what that a value is, so we're going to plug and chug. That's going to go into f of x. 0 is going to go into x. So we're going to have 50 million, huge number, equals a times 200 times negative 500 squared. And the reason why is because 0 plus 200 is 200, 0 minus 500 is negative 500. And then we see 200 times negative 500 squared is actually exactly 50 million, which means that a is actually 1 in this case. So we can rewrite the function as x plus 200 times x minus 500 squared, boom, done. A rectangle has a length of 10 units and a width of 8 units. Squares of x by x are cut out of each corner, and the sides are folded up to create an open box. Express the volume of the box as a polynomial function in terms of x. So here is our rectangle. We'll say this side is 10, this side is 8, and then they're cutting out little squares. So the squares are going to look like this, and they're going to be x by x. And then what's going to happen when this is folded up is it's going to look like a rectangular prism. So I'm going to draw it like this. It's going to be a box that's going to have an open top because, you know, this is going to fold up like this, and that's going to, this side here, right, for example, would be like this side, something like that. So what the length of this side then becomes is 10 minus 2x because I'm subtracting an x and an x from that 10. Likewise, this length here, let's see if we can make some room, would be 8 minus 2x because I got 8 is the whole length, and then I'm subtracting x and x, so 8 minus 2x. Last but not least, we have the height, which of course, when you fold it up, it's going to be this length here, x. So now my volume will simply be 10 minus 2x, right? That's the length, times 8 minus 2x, that's the width, and then times x, which is the height. Now, this is a sufficient answer, but in the book, in the answers, they have it actually all foiled out, so we're going to do that right now. We're just going to distribute or FOIL like so, and we've got 80, then we've got 10 times negative 2x, which is negative 20x, then we got negative 16x, right? Negative 2x times 8, then we got negative 2x times negative 2x, which is positive 4x squared. And then all of this is times x. First, I'm going to combine these guys, right? Negative 20 minus 16 is negative 36x. And then let's distribute that in, and let's see if we have enough room here. And by the way, I'm going to put this in the right order in terms of highest degree to lowest degree. So x times 4x squared is 4x cubed. Then I got x times negative 36x, which is negative 36x squared. And then x times 80 is 80x for the win. Boom, done. A square has sides of 12 units. A square's x plus 1 by x plus 1 units are cut out of each corner, and then the sides are folded up to create an open box. Express the volume as a function in terms of x. So we're going to draw out a little diagram, and this is a 12 by 12 square, as they said there. And then we got little squares that are cut out of each corner like so. And the dimension of these squares are x plus 1, x plus 1. And then when we fold this up, I'm going to make sort of a little rectangular prism here. You see that on this side, it was 12. Now it's 12 minus x plus 1 minus x plus 1. So we can say it's 12 minus 2 of those x plus 1s, and we'll simplify that in a second. And this is going to be the same thing because it was a square, right? So both sides are going to be the same, 12 minus 2 times x plus 1. And then the height is this nice x plus 1 because it's just this length here. Now to simplify this, we're going to distribute and combine like terms. So it's 12 minus 2x minus 2. Combining those gives me 10 minus 2x. And again, this is going to be the same as this when you simplify it. So now let's get the volume. So we got length, right? 10 minus 2x times width, which is the same thing, times the height, which is that x plus 1. Again, this is a fine answer, but in the solutions, they foiled it and simplified it, so we're going to do the same, and it's just going to take a little bit of work and algebra, but let's do it. So for this first multiplication, I've got 100 minus 20x, right, which would be minus 40x, and then negative 2x times negative 2x is plus 4x squared. And then this whole thing is being multiplied by x plus 1. So then as we FOIL, we get 100 times x right there. We get negative 40 times x, which is negative 40x squared. Sorry, we don't have a lot of room, so I'm kind of writing small. And then we got 4x squared times x, which is 4x cubed. And then we've got the other ones multiplying the 1, so that I've got positive 100. I've got negative 40x, and I've got 4x squared times 1 is 4x squared. So now we can combine some of these like terms, right, and put it in the right order. So I'm going to kind of do this in one step. We're a little short on room here. So 4x cubed is chilling by itself, so that's the leading term. And then we got 4x squared and negative 40x squared, that's negative 36x squared. Then we've got negative 40x and 100x, which is 60x. And last but not least, we got that little 100, which is positive 100. So we got to kind of scrunch together, but there is the final answer. Done. A right circular cone has a radius of 3x plus 6 and a height of 3 units less. Express the volume as a polynomial function, and they give us this nice volume formula. So here's our cone, and we're going to say that radius is 3x plus 6. And then it says the height is 3 units less. So 3 units less than this is going to be 3x plus 6 minus 3, which is just 3x plus 3. Now we've got everything we need. Let's plug and chug. So now we're going to plug in that radius right here because the radius is what is being squared. And then we're going to plug in that height, which is 3x plus 3. Now I'm going to FOIL this first. So we're going to multiply across. We get 9x squared. Then we're going to get 18x and 18x, which is 36x. And then 6 times 6 is 36. Then we're going to multiply it by that height, which is 3x plus 3. We're going to FOIL across. We're going to do a big FOIL here. 9x squared times 3x is 27x cubed. 9x squared times 3x is, times 3, excuse me, is 27x squared. 36x times 3x is 108x squared. 36x times 3 then is again 108, just x. And then again, we have 36 times 3x, which is another 108x, and then 36 times 3, which is one more 108. Now we're going to combine like terms, and we still got that 1/3 pi. So we got 27x cubed. 27 plus 108 is 135x squared. 108 plus 108 is 216x. Plus that last 108. Okay, now the cool thing about this is that every single one of these terms is divisible by 27, right? So the last thing I'm going to do, since this is all multiplied by 1/3 pi, I'm going to divide everything by 27. And when I do that and I pull it out and I multiply it by 1/3, 1/3 of 27 is actually 9. So the final form is 9 pi, and then inside we have 27 divided by 27 is just 1, so we have x cubed. 135 divided by 27 is 5, so we have 5x squared. 216 divided by 27 is 8, so we have 8x. And then 108 divided by 27 is 4. So our final volume formula, or volume function, I should say, or we can just call it f of x, is 9 pi times x cubed plus 5x squared plus 8x plus 4. Boom, done. I hope you guys enjoyed this video, and if you did, please click that like button. And if you want to see more from the Scalar Learning channel, make sure to click subscribe. Thank you guys so much for joining, and I'll see you in the next video. Take it easy.